My dear friends, welcome back to Bee Spice. In this session, we'll continue with PRV sizing procedure. Okay, so sizing procedure in the sense how to define the protected system, then how to locate the relief devices, and how to define the overpressure scenarios, and how to choose the relief device type, and also acquiring the data. What are all those data needed? Okay. Then we'll come out with the design basis. And finally, we proceed with the design session. Okay. So again, this is more of a procedure. Okay. Yeah. So somebody, need the design calculation, you can comment. I will support. Okay. Right. So in this session, I will limit only the sizing procedure, meaning methodology. In fact, one of our BSpace member has actually requested for this. That is why I'm uploading this video. Of course, it's for everybody. Okay, let's move on. And of course, before going further into the agenda and detail, I would like to thank all of you for your continuous support, friends. Okay, yeah, as I said earlier, this agenda is more of a relief sizing procedure. In fact, we already focused on intro part, the relief device basics, the design sizing terminologies, and most important, the ASME boiler, pressure vessel code section 8, all these we have covered. So this part is more of relief sizing procedure. Then relief device sizing. If somebody needs this, yeah, you can comment and I will support. We'll try to support. Yeah. Okay, so define the protected system. Okay, the first step in the design procedure is to define the protected system and understand the operation of the process, right? So hope you agree with that. Yes. So the protected system may include several pieces of equipment, meaning, for example, take a case. If the relief is provided on top of a distillation column, okay, it may protect the column and also the reboiler, condenser, accumulator, right, friends? So this is how we need to, define the protected system. So the design procedure is more complex for process involving connected equipment with different pressure rating. So that also we need to watch out. Okay, take note. The relief designer needs to have a good understanding of the operation of the process. So designer in the sense when we are given this assignment, yeah, we should have a good understanding of the process to assess the overpressure protection needs. Okay, so now we will see the locate the relief devices. Okay, so where the overpressure is protection is needed. Okay, for example, friends, as you can see here, this one, you see all pressure vessels require overpressure protection. Okay, and of course, I'm going to explain this one by one, but I'll just run through it now. All low pressure storage tank require pressure and vacuum relief also for normal operation. For example, pumping in and out and tank breathing, caused by the temperature changes, all these. Tank must also protected from any emergency event that could create an abnormally high venting load. For example, fire exposure or, procedural failure during line blowing, all these. Okay. These are the some of the scenarios wherein the pressure relief devices needs to be, considered. Then you take the case of positive displacement pump, compressor, turbine. These all requires relief devices. Okay, on the discharge side. Okay. Then segment of liquid filled piping that have a high risk of overpressure. What is that due to? Thermal expansion, right? Unloading lines that also should have a relief devices. Then piping that can be overpressurized due to the process control failure. For example, high pressure steam let down control into a low pressure steam header. Okay, these also need a relief devices. And finally, a vessel jacket is usually considered a distinctly separate pressure vessel, and it also requires its own overpressure protection. Okay, I'll explain this one by one. Yeah. So the codes and standards set a different requirement for different types of equipment. Okay. For example, if you remember the previous video, we talked about the ASME code, right? Yes. So all pressure vessel must be protected from overpressure per ASME code. Okay. Protection may also be needed for other equipment in the process where damage or personal injury can cause by excessive pressure. Okay, friends. So I hope this is clear, right? Where to locate a device. Of course, I just given only some few. There are many more. This is for understanding, just for understanding. Okay, now we'll see one by one. Okay, now we talked about this, right? Low pressure. So, low pressure tank required both vacuum and pressure relief devices, since these vessels are not designed for full vacuum, right? So, the point is low pressure tank, storage tank required both vacuum and pressure relief device. So, relief device for these tanks are designed only for vapor relief, okay, and not for the liquid discharge due to overfilling. Just remember, friends, relief device for these tanks are designed only for vapor relief, not for the liquid discharge. Because for the liquid discharge, this overfilling, we should have a, what do you call a tank overfilling protection kind of, projects, or maybe a procedural safeguards to mitigate the overfilling scenario. Okay, same case. We will have a overfilling scenario, like we will have a LT. So based on that, level, then yeah, it will trigger an alarm, for closure of valves. All these kind of safeguards we can do it. So the point is, relief devices for these tanks are designed only for vapor relief, not for the liquid discharge. Okay. Then pumps. Pump can be overpressure to downstream equipment, right? Yes. So all positive displacement pumps should be reviewed as a potential source of overpressure. Okay. Normally, relief device on a pump discharges to the inlet side of the pump, either to the pump suction pipe or the suction vessel. Okay. Relief device on a pump discharges to the inlet side of the pump. Okay. So routing to suction vessel is recommended to reduce the risk of dangerous heating of fluid caused by liquid recirculation through a blocked pump. So this is also one of the scenario we need to watch out for while sizing, locating the relief device. Okay. So this is about the pumps. Then we have overpressure hazards of process lines. Sometimes, we overlook the process lines. Any blocked liquid filled line poses a risk of overpressure, friends. If the liquid, can be heated by ambient temperature and sun exposure. So that is also very important. Overpressure hazard for process lines. So here, for example, heat raised liquid fill lines typically require a relief device or an open outlet to allow for liquid expansion. So the heat raised liquid fill line also require a relief device. And additionally, the long pipes actually. Yeah, this is, I think, some typo error, I believe. Lines, I think. Yeah, lines, it's not times. Long lines, like meaning more than 300 feet, that are not in continuous service, generally need protection from liquid thermal expansion. So this is also we need to watch out for. Okay. Now, I'm going to explain with the help of an example for a better understanding, just for a better understanding. Okay. So this is the case. You can see the positive displacement pump is used to load the vessel contents. Okay. Right, friends? Right. So cooling coil inside the reactor here, the cooling coil inside the reactor control the reaction temperature, and the reflex condenser provides additional temperature control. Okay. Yes. So here relief devices may be required at 4 locations to provide overpressure. So we will see what are all those. On the reactor itself, okay. to protect the reactor vessel and process side of reflex condenser from overpressure. So on the reactor itself. Then on the cooling water coil inside the reactor here, cooling water coil inside the reactor. For example, if the hot liquid is pumped into the reactor while the cooling water valves, these are closed, the liquid inside the tube will expand and likely damage the tubes. So there also we need to have a cooling water coils inside this what do you call reactor. So this is the second scenario. Then fourth scenario, third, on the coolant side of the reflexor here. I think here, right? Yes, coolant side of the reflexor, because hot vapor from the reactor can cause actually the water to expand and create a overpressure if coolant valves are closed. So this is also one of the place we need to have a relief device on the coolant side here. On the pump outlet here, as closing here, pump outlet. Closing the outlet side valve may damage the pump and discharge piping here also. Okay. I think I only put it here, but there are four scenarios here. So likewise, friends, we have to actually see and check where all the pressure relief requirement is needed. Okay. So now we have know where to mount all these actually. Now we need to define the overpressure scenario. See, for each process of equipment, there are typically multiple scenario, right? So now for that we need to have a let us be entity. Okay. So when evaluating the scenario, consider the modes of operation rather than normal operation, such as other than normal operation, startup and shutdown. Of course, we are also focusing on startup and shutdown, but we also need to see the modes of operation. That is a point. Once the potential scenario are defined, the next is to determine the credible scenario. See, what is credible scenario? Credible scenario is typically the one that involves a single failure, right? Scenarios that require multiple independent failure are typically not considered when sizing individual relief devices. That also we need to take note. Okay. I hope this defining the overpressure scenario is clear, right? Okay. Few more to add on. See, we talked about the credible scenario, right? It's typically the one that involves a single failure. Here, credibility, is based on the risk, friends, which is a function of probability and the consequence, right? I hope you agree. So for that, we need to have we have a formal hazard identification procedure, such as LOPA, HAZAP, FTA, fault tree analysis, and failure mode event analysis. All these can be used to assess the risk. So most relief design involve also some compromises. Compromise in the sense, a particular relief device might work fine for a primary design scenario, meaning for controlling, but it poses a performance risk for the other scenario. See, for example, this is a relief valve that is sized for vapor scenario, but it must also work effectively in liquid scenario, right? Yes. So the liquid scenario will often present some mechanical instability risk, which must be tolerable to the plant owner. It may require lower pressure to reclose in liquid service. So that is also we need to watch out for. Okay. So it is possible that no causes for overpressure can be identified for a particular piece of equipment in a processor. When we do the, identification, it is possible that no causes for overpressure can be identified. But the ASME boiler and pressure vessel code section 8 requires all pressure vessels to have a protection from overpressure, regardless whether there are any credible scenario. Okay. So the relief device is installed, to be installed for a pressure vessels, all pressure vessels as per this code. Okay. So these are the defining the how to define the overpressure scenario. Okay, right. Now we are already done with the scenario. Right. Now what we have to do? Choose the type of relief device. Right. So yeah, relief device for a specific application. Because why? The sizing depends on the type of relief device selected, right, friends? So as you know, most common are spring operated relief, balance spring operated relief, rupture disc, pilot operated relief. Okay, these are the most common, right? So here the rupture disc and buckling pin type relief device do not reclose after activation. So there is a challenge with this rupture disk and the buckling pin type. So we should not use that for the first choice. So preference should be given to reclosing relief devices. Again, a typo error for both and safety reliability. Okay. So here the routing of relief device effluent is also influence the selection of relief. We are talking about this rupture disk and buckling not preferred because it should not, it should not reclose, right? So, additionally, friends, of course, we are talking, we are telling that spring operated, balance spring operated, all these are primary choice. But one thing we need to also consider is the routing of relief device effluent, you know, also influence the selection. How, see, for example, you see, if the device discharges to atmosphere, then conventional spring relief valve is generally the best and of course in economical. But if the discharge is routed to a containment, for example, to pipe or vessel, or a treatment, for example, flare header, then a balanced or pilot operated relief is more appropriate due to the back pressure from the downstream system. You got it right? Yes, that is the understanding. Okay, friends. Now you know how to choose the type of relief device for which application. Okay, good. Now we need to acquire the data. Obvious, right? Yes. So, for example, a control valve failure scenario requires knowing the knowledge control valve's flow coefficient and upstream pressure. So this also, for example, if you are dealing with a control valve failure scenario, it requires a control valve flow coefficient and upstream pressure. If the overpressure is caused by centrifugal pump, okay, then pump curve and size of the impeller need to be needed to calculate the flow rate, right? Okay. Then to calculate the required relief area, okay. Then physical properties such as capacity, density, heat of vaporization, and vapor pressure are needed. Okay, friends? Yes. So these are the data needed for the relief valve sizing. Now, we need to also determine single phase or two phase. We have talked about this in the previous video, right? Yes. So, here at this point of relief design process, a determination must be made as to whether the material entering the relief device will be a single phase or two phase when the device is at the relieving pressure. So, if a chemical reaction is involved, two phase is very likely. During fire exposure, two phase is also possible, but not likely unless the fluid is inherently foamy or having a high liquid viscosity. Okay, just take note. Then another one is the superficial velocity in a narrow diameter vessel may also result in two-phase flow. I think again a typo error. Sorry for that. Two-phase flow if velocity is too high to allow for liquid disengagement. But again, friends, this two-phase flow is very complex and yeah, it needs a lot of study and expertise. Let's just take note. So that's about the determining single or two-phase flow. Then now we are all done with that. Now we need to determine the design basis for the device. Meaning, design basis include the mass discharge rate through the device and operating information for the relief. What is that? Relief set pressure, overpressure, superimposed back pressure. So design basis includes mass discharge rate through the device. How much mass is discharged through the device, and also the operating such as relief set pressure, overpressure, and back pressure. All these also needed. Okay, for rupture disk, burst temperature is also needed. Okay, just keep it in mind, friends. These are the design basis. The scenario that requires the largest area rather than the one with the highest mass flow rate is controlling the case of device sizing. That is important. The scenario that requires a largest area is the controlling case for device sizing. Liquid relief scenario commonly have the highest mass flow rate, but they are generally not the controlling scenario when vapor scenarios also exist. That is also we need to take note. Liquid scenario commonly have the highest mass flow rate, but they are generally not the controlling scenario because when vapor scenario also exist. Okay, so these are the determined design basis. Okay. So now we are almost done everything, my friends. These are the things. So next, relief device sizing. Basically, sizing means, of course, I don't have any software and all, but yeah, I can do some, calculation using formulas and all based of each application, whether it's a gas, I mean, a liquid, gas, all these. Okay. So let me know if you want. Otherwise, I will just wind up with PRV. I'll focus on some other aspects. Okay, friends. Thank you and take care. Bye bye.